Hi, everyone. This is the third talk of Higher Structure Seminars under Feza Gürsey Institute. Today, our speaker is Professor Urs Schreiber, who is affiliated with NYUAD at Abu Dhabi and Czech Academy of Science at Prague. He completed his PhD at University of Duisburg-Essen in 2005, working under Robert Graham, with the dissertation titled From Loop Space Mechanics to Non-Abelian Strings. And today he is here to give us a talk about higher and equivariant bundles. Let's welcome him.
Thank you very much for the invitation, for giving me the opportunity to speak in a nice seminar. Right, so I'm going to speak about higher bundles and their equivariant version. And what I'm going to do is I give a gentle exposition of just one basic concept that underlies a series of articles we have written on this topic. I'm not planning to go into deep theorems in these articles, but when I was thinking about what to say, I thought maybe I should take the opportunity and start at the beginning and give an exposition of basic material that all this rests on. But I do want to give one brief motivational slide, which serves all of the motivation, an overview, summary, and an outlook, what I'm going to do. So there would be much more to be said about these things, but speaking of higher bundles, I want to make one point in this talk, and I'll try to illustrate this very concretely with a handful of examples, very easy examples that I'm going to show later. Namely, the point is that the interest in higher fiber bundles, and higher principal bundles, and their variance is really due to their role in describing generalized cohomology theories. And by generalized cohomology theories, I mean something slightly more general than what is commonly in algebraic topology called generalized cohomology, where it usually refers to generalizations of ordinary, say, integral cohomology by going to theories that are represented by spectra. So these are abelian theories. What I'm going to talk about here, and I'm going to show this in simple examples, is something that is a bit more general still. So it's concerned with non-abelian cohomology, and this will be the fact that our fiber bundles, those higher bundles, have general fibers, not necessarily fibers that are themselves higher abelian groups, but could be non-abelian groups. The cohomology theory is going to be twisted, and that is actually reflected in the fact that you have bundles in the first place. So that say principal bundles. Then there's differential and equivariant aspects of these cohomology theories, which is where the equivariance of these higher bundles comes in. So the point I will try to illustrate in examples is that a higher bundle is something that has as a fiber the moduli stack or classifying space of a cohomology theory instead of just a set or just a group as for ordinary bundles. And as such, it's something that locally modulates a cohomology theory and globally has some twists. So that's what motivates us here, what these higher bundles are really good for. But I do not plan at the moment to speak much more about this. I just want to highlight this at the beginning. And instead, I do want to go into the foundations of how to set up these higher bundles in elementary detail. So I want to walk you from scratch through just the definition of equivariant principal bundles with some simple but key examples. And for the time being, so there's some theorems here that one could discuss, but for the time being in this talk, I just want to kind of make the claim that the definition I'm presenting is a good definition in the sense that it's transparent, you know what you're doing, it's elegant, universal, like claiming that everything you ever want to do with it is captured. It's generalizable in various ways, so one can add supergeometry and other directions to it. And maybe most importantly, it's actually practical. One can actually use what I'm going to present here for kind of connecting between abstract theory and concrete detailed computations. All right, so I'm not quite sure what the audience's background is, but I do assume, since it's a higher structure seminar, that you're all familiar with some higher groupoids. But let me just briefly mention the two groupoids that we're going to use, crucially. and introduce some examples. So two groupoids, as you know, so higher bundles exist for any degree up to infinity, which is why these articles that I mentioned at the beginning have all these infinity signs in them. Principal infinity bundles. This infinity sign is for the homotopical degree, whether we're using two groupoids, three groupoids, up to infinity groupoids. But in this talk, for illustrational purposes and to have something concrete to hold on to, I'm going to focus on two groupoids. So two groupoids are, if you wish, the algebra of two-dimensional pasting or compositional operations, as illustrated by this cute little cartoon picture that I'm showing here, which you might think of as being a picture of how pieces of surface in a topological space, two-dimensional images of some two-dimensional space in topological space can be composed along their boundaries. This can be seen as a cartoon picture of what you might call the fundamental two-groupoid of a topological space. But we're actually going to be concerned mostly with even more simple examples. So this example here in its generalization will drive, simple as it is, will drive this theory. So for G, just an ordinary plane group, at the moment without extra geometric structure, so think of just a discrete group, cyclic group or something like this. Then of course we have its delooping groupoid, which in the previous pictures is just the thing that has a single vertex depicted by a bullet here, by a dot, which has a one-dimensional edges labeled by the group elements, GI, and which has two cells whenever the edges, the three edges of such a triangle compose to each other. So if one is labeled G1, the other is G2, then their composite is G1 times G2 done in that group. And that will give us such a two cell in our two groupoid, which since it's just sort of the identity of two cell might then just be called a one groupoid, even though it's a special case of a two groupoid. If our group is abelian, in which case I'm going to denote it by A. By the way, can you see the right side of my slide, or is it hidden behind our videos? For me, it's kind of hidden. Maybe I can move this. So, So if the group is abelian, then we can boost up the dimension here, not label the edges of our two groupoids with the group elements, but label the surfaces, the two-dimensional cells. These surfaces can be composed in two directions, vertically and horizontally, and this is only consistent if the group elements commute with each other, which is why we need an abelian group to make sense of this. In this case, we have a two groupoid, which I'm going to denote by B, boldface B, BA. So this B sign is going to appear throughout this talk. The boldface B is supposed to indicate that we're dealing with a stacky or groupoidal version of what the topologists like to write without the boldface as BG and call it the classifying space of a group. So it turns out that one can take geometric realizations of these groupoids, and if you geometrically to make them topological spaces, and if you do that to BG, you get what is usually called the classifying space, BG without the boldface. The boldface is supposed to remind us that we're actually working with something that's a little bit richer than just the classifying space. It knows about the classifying space, but there's a stacky aspect to it. It's also actually simpler. So that will be a companion to us throughout this talk. Here's a more interesting example, slowly climbing up the ladder of interestingness. If we have a group G which acts on an abelian group by linear maps, so by group automorphisms, then we can form something like the semi-direct product of the previous two examples. We can take the two group BA that we had on the previous slide, which had two cells labeled by group elements in A, and we can take the semi-direct product with the group G regarded as labeling edges, and then we get this mixture of a two groupoid whose edges are labeled by that possibly non-abelian group G, whose two cells are labeled by abelian group A, where the vertical composition is just a group operation in A, which I write additive. But with the horizontal composition, there's this funny extra twist. It's the semi-direct product group operation, an ordinary semi-direct product of G with A. So when you multiply this way, the second summand of A gets acted on by the group element G1 by its given action. So we can check that due to the fact that the action is by group automorphisms, this is actually consistent in that if you have four cells forming a square, it doesn't matter which order you compose them, whether you do it first vertically and then horizontally or the other way around. So this is a consistent two groupoid which I'm going to call it. So one can either think of it as being the delooping of that semi-direct product group, or, and I'm not going to explain this much in this talk, even though it plays a big role, but I'm just going to throw this notation at you. One can also think of this as being the homotopy quotient of the two groupoid, the double delooping of A by the group action. It's actually the same. But take this just as notation if you wish at the moment. So this is actually a special case. I'm just going to focus on this special case in the coming examples, but maybe just to highlight that this semi-direct product group here is a special case of a general construction that is known as the, or yeah, I guess known is maybe a big word here, but some authors, including us some years ago, called it that way, the automorphism 2 group of group gamma. I suppose this goes under different names too. So where the underlying one groupoid is just the automorphism group of our group gamma, labeling the edges here. And then two morphisms are labeled by the actual underlying group and regarded as being inner automorphisms, taking an automorphism to its composition with that inner automorphism. So here I'm replacing for a moment, I'm kind of resolving the dot that appears everywhere by B gamma to highlight that you should think of this as being actually a morphism from B gamma to B gamma, even though I haven't quite explained how that works. But if you, I mean, you've seen groupoids. So this is actually, you can think of this alpha as being a functor from this delooping groupoid to itself. And these are the natural transformations. And if you work out what this means, one sees that one gets this composition law for this automorphism 2 group. I need to move my videos again here. Okay. So the previous construction is actually a simple kind of semi-abelian version of this more general automorphism 2 group. And you realize that I changed the order of the arrows here. This is something one has to deal with in this business all the time. One has to make a choice actually whether all the group actions that appear are from the left actions from the right, which translates to whether or not the multiplication of the group elements goes with or against the order in which we compose these arrows. This is not something to worry about here, just to mention in case you're wondering how things are labeled. Before long, we're going to have two groups that act. There's a structure group of our bundles that will act from the left in my convention, and there's an equivariance group that will act from the right. But not to worry about, just to highlight this. So one point I want to make here. So in a moment, I'll show, that's what I'm working towards here. I want to indicate how principal two bundles, higher bundles for this semi-direct product structure group really encode something completely well-known, namely it computes ordinary degree 2 cohomology with local coefficients. So this will encode something that people know as an abelian cohomology theory. But I do want to highlight that as a 2 group, this thing is actually non-abelian. I mean, as you can see here, the horizontal composition law of that 2 group is just the law in the semi-direct product of groups, which is non-abelian as soon as the acting group G is non-abelian. This will be a running theme in what I'm talking about, or at least what I'm secretly headed towards, is namely that it seems somewhat underappreciated that there's a big role of non-abelian cohomology theory in the sense of Giraud and its further generalizations, even within ordinary abelian cohomology theory, like Whitehead generalized cohomology theories, as soon as you start adding bells and whistles. Namely, we will see that as soon as you have an abelian cohomology theory, which is twisted and or equivariant, then the actual classifying spaces are going to be non-abelian, just certain fibers are abelian. So that's an important point I want to make. And another point, which maybe is not too important for what I'm going to say is, but maybe just as an illustration, is that these groups, these two groups that I've shown so far, sit in fiber sequence, in fact, a homotopy fiber sequence, where on the right we have this BG, whose edges were labeled by G. Then here in the middle, I mean, it's a really simple example, but this is an example of general pattern that is quite important. So in the middle, we have this semi-direct product group with these labels, and on the left, just the doubly delooped A. And before long, we're going to see that, yeah, this is actually an illustration of what I just mentioned. We're going to look at maps into this thing here, which is really a non-abelian object. But if we fiber that over BG and just look at the fibers are actually an abelian object, which will actually, as we'll see, classify abelian second cohomology. Okay. So I'm just going to say it informally here, but you've seen all this before, I guess. A two-functor, of course, is a mapping between such two group hosts that respects their structure, hence identities and composition. And instead of just writing it on formal definition, which is boring, I'm going to actually highlight a simple, interesting example of two functors, which we can already talk about now. We see there's already something interesting going on. So consider the group, the abelian group of the integers, the simplest thing we can do, but equipped with its Z mod 2 action by automorphisms, by group automorphisms, hence by sign inversion. So that's just a reflection action of Z mod 2 on the integers. And we consider any group, discrete group, equipped with a group homomorphism to Z mod 2, so that it can act via this homomorphism on the integers. Then the second we can consider, it's a classical concept, the second degree 2, group cohomology of G with coefficients in the integers regarded as a G module via this action, right? G maps to Z mod 2 acts on Z, so Z becomes a module over the group G, and we can ask for the group cohomology. And I claim, it's a little exercise now, and I'm going to show the diagram in a moment, that two functors from BG to this semi-direct product group, as defined on the previous slides, such two functors are exactly co-cycles in that group cohomology. So here I spelled out how this works. And this is super elementary, and maybe you've seen this before, and then it's really boring, but since it's really important to see the inner workings of all these higher structures, I'm just going to go through this for a second here to illustrate that something important is already happening with these super trivial examples. So on the left, I'm just drawing pictures of BG. Right, BG was just a thing that had a single vertex, of which I'm just drawing these several copies here just to ease visualizing it. The edges are labeled by the group elements. And right, whenever two of these compose, we have the edge labeled by the composite, by the group operation composite. They're just equal here. There's an identity two cell here, but I'm still writing it, drawing it as an actual two cell. This is important. If you've heard of Kahn complexes and stuff, of course, what I'm really drawing is I'm drawing the nerve, what people like to call the simplicial set, that is the nerve of BG. But this is just terminology that isn't really actually needed to understand what's going on here. We have these group elements and they compose. And the fact that the group operation in G is associative means that these two pictures are actually the same two cell, the same two morphism in BG, right? Because it doesn't matter whether we first compose G1 and G2 to G1 times G2 and then multiply with G3 on the right, or we do it the other way around, first composing these two. And this identity, as we map it over with our two functor, so our two functor, which is really, if you wish, homomorphism of simplicial sets, it has to respect all the structure here and has to map it to our semi-direct product delooping here, whose edges now, remember, they are labeled by elements in Z mod 2 in this acting group here. So this is sigma of G1 is the image of this edge in Z mod 2 is some sign. So here's a sign, the edges are labeled by signs. The two morphisms, remember, are labeled by elements in A. And there was this one single law, and that is now important, that if we whisker it, some people say, if we have a one morphism here on the left, composing with a two morphism here, then that two morphism kind of gets transported along that one morphism to the common endpoint on the left. So it gets acted on by G1. So that means in our pictures here, that as we add up these two cells here, remember adding up in B2A is, well, composing two morphisms in B2A is just adding up the labels. So we're just adding up this label with this label, and this has to be equal to the addition of this label with this label, but this is one, you see my mouse, right? I mean, if I'm pointing here, you see it, right? So there's this one edge here. So this is one two cell, which is not, this is the single two cell whose leftmost vertex is not the bottom left one. You know, all the others have this bottom left vertex, so they're kind of all based here. But this one, just to give an intuition what's going on, kind of needs to be transported along this edge to be compared to what's going on here. And that action, well, that gives an action of this sign on this group element. If you now open the textbook on defining group cohomology, you see which formula we get. So C of G1, comma G2 plus C of blah, blah, blah has to be equal this C plus finally that action on this C, then that's exactly the formula of a cocycle in degree 2 group cohomology with coefficients in this module. We see it's just a two functor from our group to this coefficient group, which is fibered here, so it has to respect this triangle, which just means that we want these edges here to be labeled by the prescribed twists. we could omit this and just consider any functors, and then we could project out and ask, well, what are they assigning to the edges? So there's no real restriction of generality here, but to map to standard context, one can draw it this way and have the statement that, yeah, the group, to say once more, the degree 2 group cohomology of G with coefficients in this module is exactly the equivalence classes of two functors of this form. So this is trivial as it may be. This is the blueprint of really all the statements that are going to follow. We're going to boost this by replacing BG by the Czech groupoid of the homotopy quotient of a smooth manifold acted on by G, and add some other bells and whistles, but the pattern will really remain the same. We will see that two functors from here to there encode co-cycle information. All right. So I mentioned already, we want to be talking about smooth manifolds before long. So let's say, what is a smooth two groupoid? And what I'm going to say now here is really trivial in itself, but there used to be a time, and maybe the time is still now, I don't know, where the community was actually struggling with how to make good sense of, you know, Lie two groupoids and the smooth versions. Here's the general way that is the right way to go about it. So we say a smooth structure on a two groupoid as before, and I'm going to draw it as calligraphic X, is a rule. So it's a slightly non-standard definition if you haven't seen diffeological spaces or so. So we're not talking about manifolds. So we're just asking, well, how can I see that there are smooth families of stuff in my two groupoid? So I say for every chart, every Rn, for any n, the smooth structure is a way to assign a plane two groupoid, as we had before, which we're going to think of as the two groupoid of probes, of ways of probing our would-be smooth two groupoid with Rns, ways of mapping Rns into it, and you know, transforming these. We'll see examples in just a moment. And then, of course, we want to make this functorial. So if you probe with Rn1 and you probe with Rn2, there's a smooth function between these Cartesian spaces, just an ordinary smooth function. Then, of course, every probe by Rn2 gives a probe by Rn1 by just precomposing. And so this precomposition operation should give a two functor from this two groupoid of probes by Rn2 to this two groupoid of probes by Rn1. And we just ask if this is actually a functor. So it respects compositional identities. So the way to think about this is we have this thing, which is really defined by what I'm describing here. It's going to be a smooth two groupoid. It has a two groupoid of probes by points. So that's just its underlying points and their symmetries. And then we have a system of how to ask what's a smooth family, say a one-dimensional smooth family of these points, or a two-dimensional smooth family of these points. And that's answered by these high-dimensional probes. And that structure, that information is the smooth structure, or two groupoid. So what I'm describing here, you know, depending on your background, I don't know, might seem a bit exotic, but this is actually what Grothendieck way back in 1965, starting in 1965, advertised as functorial geometry. Here's some text there, which you can see when you follow this link to the NLab, where he makes strong statements where he says, people, please forget the original definition of schemes. Let's think about them this way. And of course, that's his functor of points point of view. He didn't talk about Rns, but about wide varieties here, but the idea is entirely the same. And in jargon, which is really unfortunate, I think, but quite common, what I'm describing here is, of course, what people like to call a pre-two stack. And in this case, it's on the side of Cartesian spaces, but all this jargon really, I think, serves to not make transparent what's actually going on here, which is really this picture. So here's a simple example to keep in mind. So if we have an actual smooth manifold, then of course it's going to be a smooth two groupoid, stack incarnation if you wish, simply by this rule. So we have to say what's the smooth families of ways of mapping Rns into it. And of course we take it to be the ordinary ways of mapping Rns into it. So we will regard now a smooth manifold as a rule that sends Cartesian spaces to two groupoids, and it does so in a rather trivial way. It sends them all to constant two groupoids that just have a single that just have a bunch of objects with only identity morphisms and two morphisms between them. And these objects, these vertices, are just the smooth functions from Rn into X, ordinary smooth functions. So this just says a smooth manifold is a bunch of points together with a rule for what it means to have Rn parametrized families of such. And it's essentially the Yoneda lemma, using that manifolds actually covered by ions. The Yoneda lemma that tells you that regarding a manifold as a functor this way of this on the category of Cartesian spaces gives you a fully faithful embedding the category of manifolds into the category of pre-sheaves of Cartesian spaces. So here's a slightly, the next more interesting example is, or maybe a slightly orthogonal to the previous one, we take gamma to be a group, which is now a Lie group. So it has smooth structure of a manifold. And that means that for each Rn, the sets, the plane sets of smooth functions from Rn to gamma, they of course have group structures just by pointwise multiplication, group operation of these functions. So these are groups. And as such, we already know that these groups, smooth functions from Rn to gamma, they define groupoids, which I used to call, or which I did introduce as boldface B of these groups. So we say that B gamma, smooth version of gamma is now the rule that 2Rn, since the groupoid of probes, which has a single object, witnessing the fact that there's a single vertex in here, and then it has a smoothly Rn parametrized family of group elements in gamma. So the picture of B gamma is exactly the same picture as before, only that the edges are now not labeled by plain group elements, but by families of group elements, and everything is parametrized over Rn. So that's smooth structure. And I don't want to be speaking too much about stacks here, just to bring out the simple mechanism behind all this. But I have this one slide here just pointing out that, of course, behind this is some theory of some stacky theory. So we don't actually need to go through this description here, but just to highlight that what I'm setting up here, these smooth two groupoids are of course going to be models for what you might either call smooth two stacks or smooth homotopy, two types, or whatever words you like. And them being models essentially means that each of them is a stand-in for what we're actually interested in. And we need a rule for whenever we want to do something with these smooth two groupoids, say we want to map one to the other, or we want to compute something like homotopy fibers between them, we just want to make sure that we found a good representative. And there's some rules here. The rules of model category theory, of course, they tell you what is a good representative and how to replace a non-good representative by a good one. And we're just going to see this in concrete examples without fully going through the full rules here. But I'm going to employ the following fact, which is a theorem, if you do introduce some model category theory, but which for our purposes, we can just take to be a definition. Namely, the rule will be that we will want to be asking for like the most general maps between our smooth two groupoids. And that will require that we replace our domain groupoid by a good one, which we're going to call a cofibrant one. And we'll see the only single example that we need in just a moment. And then in order to compute the homotopy fibers, what we're going to do is we want to ask, maybe here's a point in the domain two groupoid. And what we need to do is, in order to compute the homotopy fiber over that point, we need to replace that point with a fibrant two groupoid, a smooth two group that sits by projective fibration over this guy, and then form an ordinary pullback. So that's the rule I'm going to use for those who are interested in the stacky picture. But yeah, this is just to indicate that there is a rule set behind this, but we don't have to worry about the full rule set to just understand what's going on.
If I could interrupt for a second to make
yes,
a point.
Please.
Yesterday we had like an informal lecture, and in that context, somebody asked whether these kind of model structures underlying the infinity categorical constructions and higher constructions are actually computationally or otherwise relevant. And I didn't come up with an example then, but to just point out to the audience, if that person is still here, that here is the example of a model structure that's serving like a computational purpose, kind of guiding concrete application. So that was an open question yesterday. So I thought.
I see, thanks. Yeah, that's a very good point. Yeah, exactly. I'm going to walk, if you wish, I'm going to walk you through concrete examples for how exactly this theorem in model category theory will produce the theory of higher principal bundles for us. It's really this rule here for how to compute. We will see that this rule that you have to replace a point by a fibrant replacement, this rule is what gives universal principal bundles. We'll see this on the next two slides. And then the fact that we have to replace domain objects here by cofibered ones, that's really what gives Czech cocycles. Oh yeah, so this is actually important. This is part of why I made this bold claim, somewhat overblown claim maybe at the beginning somewhere, where I said that what I'm presenting here is what I truly believe to be the good definition of going about things. You set up an easy way of talking about higher group points, equivalent geometrical structure, and you do have some model categories in the background that serves the purpose of telling you how to operate with these, what it is you need to do if you have a certain goal in mind, what you must do to achieve that goal. That is really what model category does. And that combination of having that easy functorial geometry picture together with that rule box, that rule set in the background that tells you what exactly you must and must not do, that gives a very, very good theory. Okay, yeah, let's see how this works. So I have this slide here, but this is maybe a distraction. Let me go back to this later and look at this easier example, which more directly connects to those cofibered replacements that are advertised. So let's look back at a smooth manifold. We've seen that a smooth manifold gives a smooth group void in a rather trivial way. Remember, we just remember what is the smooth ways of mapping RNs into it, but there wasn't any morphisms here. And it turns out that makes this two groupoid be a little too rigid. It's not fluffy enough in a non-technical but actually useful way. It's kind of too constrained. It needs to be a bit more relaxed in order to support all the functions that there should be, or the functors, of course, that should go out of X. So in technical terms, this X is not cofibered. It's not a good representative for mapping out of. So we're gonna improve that now as follows. So we ask that the smooth map, so we ask for a good open cover. Every smooth manifold are the usual assumptions, paracompact, second countable. Smooth manifold has a good open cover. It admits a metric, blah, blah, blah. Good. So good open cover means it has an open cover by open subsets, such that whenever an intersection of open subsets by which we cover it is non-empty, so that there's at least one function denoted here boldface X with these labels indicating into which product we map. So if there's at least one, if it's not empty, then it has to be not just contractible, as people often say, but actually diffeomorphic to an open ball. Then this is what, like in bottom 2, you will find as defined as being an open cover. The topologists sometimes just say the intersections have to be contractible, but actually for differential geometry, one needs them to be, this is a subtle technical point, which doesn't need to concern us here. It's kind of important. It actually has to be diffeomorphic to an Rn and hence to an open ball or anything. So that's a good open cover. And if we have that, from such a good open cover, we get another smooth two-group point, which I call the Czech two-group point. That might, I forget, this might be a word I and colleagues maybe made up some years ago. But anyway, that's a good name for it. I guess some people, I guess there's an old article by Ross Street where this might be called the co-descent two-group point or something. So I'm not sure if you will find this necessarily if you look at the literature, but anyway, that's a good, I mean, this term. So here's how it's defined. Its objects are, so it's again a smooth group point, so I have to tell you what are the Rn parametrized objects, what are the Rn parametrized vertices. So the Rn parametrized objects are just these things here that I already showed before. It's the smooth functions from our given chart, Rm, into a single intersection, so into just one chart, into one patch UI. There's a morphism, a unique morphism between two such functions if they actually happen to lie in a double intersection. So if one function goes to ui, the other one goes to uj, but they actually coincide as functions to x, right? ui and uj are subsets of x. Then we say, let's draw a morphism between them. Right, so this is just a simple idea that these two things want to be representatives of the same point, both with x, but they might sit in different charts. So we combine them, we make them not equal as they were in x, but we make them equivalent by adding a morphism, and so forth. So now if we have a point in ui which agrees in X with a point in UJ, which in turn agrees with in X with a point in UK. So in other words, if we have a single point in the double intersection, in the triple intersection of UI with UJ with UK, well, then we say that triple intersection is a two-morphism here. This is as two groupoids go, this is a rather trivial two groupoid. In fact, that makes it a cofibrillant resolution of our manifold. It's actually contractible everywhere, but it has a smooth structure and it's kind of more flexible now than the original manifold was. It really says, well, all these points might sit in different patches, but if they actually happen to coincide in X, then we make them equivalent via morphisms. So that's the Czech groupoid. It has the evident two functor, smooth two functor, down to X, which just forgets the patches that our points sit in, and just remembers the underlying points, which makes them all equal. So this is, as one can check, this is well, I haven't actually defined this, but this turns out to be a local weak equivalence, meaning that if you take small enough open neighborhoods in our Rn, you can actually, this is actually a homotopy equivalence between these groupoids. This is clear by this fact that everything is here connected in a unique way. If you lift this single point anyway, there's a contractible space of choices lifting. So this makes this local weak equivalence. In other words, what I'm trying to say is this Czech groupoid is, in the world of two groupoids, of smooth two groupoids, it's really the same as X. It's an equivalent incarnation of X, but it's a better model for X. We're gonna actually use this Czech two groupoid to map out. So to model two functors out of X, we're actually gonna, or to model maps of stacks of X, we're just gonna look at ordinary smooth two functors, but out of hat X, out of the Czech groupoid. So this is the first thing the model structure does for us. It tells us, what is it we have to, if X is a model for some stack, do we have a good representative for that, what it is a model of? And the answer is yes. The Czech groupoid is a good representative. Namely, here we see what's going on now. So suppose now we have a Lie group. And remember, to a Lie group, we had associated this smooth groupoid with a single vertex and edges being smooth families of group elements. And now let's look at the smooth functor from X as a stack to be gamma. Excuse me. So just plain smooth functors from this Czech groupoid. So it has to send every point in some patch to the single object here. There's nothing to be chosen here, but then every edge has to be sent to a family of group elements. So we get a function from double intersections, right? This is a point, this edge is really a point in a double intersection. This has to be smoothly mapped to a group element. And then whenever we have a two morphism, so whenever these points in the triple intersection actually coincide, then we have to find a two morphism here as its image. But the only two morphisms in B gamma were identities. So it means that the product of this group element has to equal this group element. But this is the, if you've ever seen it, this is the co-cycle rule. It says a Czech co-cycle on a smooth manifold relative to some open cover is a smooth function from double intersections to group elements such that on triple intersections, this law holds. Gamma ij times gamma jk equals gamma ik. So in this way, a smooth functor is the same thing. It's verbatim the same thing from the Czech groupoid to B gamma is a Czech co-cycle. A degree 1 Czech co-cycle with coefficients in this possibly non-abelian Lie group. And you see already where we're headed here, of course, Czech co-cycles are one way of encoding principal bundles. So let's see how that works. Here's another way to see a resolution, which is also simple, almost trivial, or it is trivial in itself, but is of key importance for this whole theory. So remember that in this rule box, this kind of undisclosed rule box, I said if we're mapping into something, we want to look at a point inclusion in that something, we want to make a vibrant replacement of it. So some good, we want to take some good representative of the point. That's what I'm going to do now with B gamma. So down here is our familiar picture of B gamma, gamma 1, gamma 2, it's up to gamma 1, 2. And there's evident point inclusion if the point is the two groupoid that is just constant, just single object, single morphism. This certainly maps into B gamma, hitting the single object. And that map is in an intuitively clear way. It's not very fluffy. It's not very relaxed. because it sends this one point to that one object. So, so we're going to blow this up a bit, make it bigger without changing its homotopy type. By factoring it through this two-groupoid E gamma, as we're going to call it, and of course the notation is supposed to be suggestive of universal bundles. The realization of this thing, the topological realization, will be the familiar, or is the familiar universal principal gamma space. But actually here in our groupoid world, in our three category of two groupoids, it's something really simple. Namely, we just say, well, let's replace this point. That's allowed to be any group element gamma. But we want to do so in a way that doesn't actually change the fact that it used to be a point up to homotopy. So we say, well, okay, whether we choose gamma or some other group element, which necessarily differs from gamma by some gamma 1, these two choices are still supposed to represent the same point. So let's make them equivalent. So we just say, okay, gamma and gamma times gamma 1 are two different objects now, but we immediately make them equivalent by saying for every gamma 1 that takes them to each other, we add a morphism. Same here, and so we make these again equal. Right, so you can also think of this groupoid here as being the action groupoid of the group gamma acting on itself by right multiplication. Objects are the group elements, morphisms are the actions by right multiplication. The point is just that this whole thing is just a very big version of something that's really the point, because everything is equivalent in a unique way. There's no homotopy here. There's no way of going around and finding some non-trivial monodromy. So this is actually a big fat point. It's locally weakly equivalent, or it's actually even globally weakly equivalent to the point. But it now maps in a surjective fashion in an evident way to be gamma. And that surjective fashion, if we go through it, so it really means this is now for each Rn Kahn vibration, this makes this a good representative of the point sitting over B gamma. So that's the second ingredient we get from the model category theory. It tells us we want to map out of the smooth manifolds. We have to replace them by Čech groupoids that don't change the homotopy type, but make them more fluffy. And if we map in, if we want to know what is the point in a target groupoid, we have to blow it up in this way. So with this in head, now I claim we get a new way, not the non-classical way, but a very good way to speak about just ordinary principal bundles. And that way is the way that will generalize to higher bundles. So we want to speak about gamma principal bundles on a smooth manifold. So first of all, we replace that smooth manifold by its Čech groupoid, because we want to map out of it. And then we've already seen that the smooth functor from the Čech groupoid to be gamma, it's the same thing as a Čech cocycle. Standard theory tells us that a Čech cocycle somehow encodes a principal bundle. So let's see how this actually works. We have the point inclusion to be gamma. We resolve it. We do a Fibonacci replacement by this E gamma thing. And now, as the notation is supposed to suggest, you want to form that pullback and say, which is actually now the homotopy fiber of the point really. And I'm claiming that this is the principal bundle. Let's see how this works. That is classified by the, let's put this up. By the Čech cocycle. So remember down here, I've already shown this on previous slides, but let's just recall it. This two functor from the Čech groupoid to be gamma has to take every edge in the Čech groupoid to a group element. So these are our Čech cocycles, gamma ij of x, gamma jk of x, satisfying this law. Up here, E gamma, remember, had group elements gamma also at the objects. So these are now also labeled, if you think of this as coming from here. So these are labeled by group elements. And if this sits over it, we have to have a representative of this gamma ij up here. So this picture is supposed to make clear now we have to form this ordinary pullback, this ordinary fiber product of these groupoids, which is just the fiber products of their objects, of their morphisms, to determine what this groupoid here is. And doing so, just by reading off and knowing what a fiber product is, we see that in the top left, we get this. We get a groupoid here. So this P hat is a groupoid whose objects combine the objects here with the objects here, namely such that they agree here. So the objects here are labeled by points x in a chart in a patch of our X together with the group element, which you're supposed to start thinking of as being the group element in the fiber of a bundle over X. But we're on a chart, so we could also say, well, what if my point actually sits also in the patch J? Well, then I have a transition function here that is associated with this transition, and the composition law in this group point here, the EG, told us, well, if I go along this transition function, I have to change my group element that used to be a gamma down here, gamma X down here. I have to multiply it on the right with my gamma ij. So it tells us that in this pullback group point here, we get objects that are labeled by points in patches, labeled by group elements. But if I change the patch, then the group element has to be relabeled by multiplying this transition function. And we're going to identify this whole thing and so forth. And if you look at this, if you've ever seen in a textbook the construction of how from a Chekhov cycle one reconstructs a principal bundle, it's exactly this equivalence relation which is divided out to form the total space of a bundle. This is indicated by this local weak equivalence here. You just take this group point here, now just take the equivalence relation that is generated by these morphisms, you find a smooth manifold, and that is P. That is the usual principal bundle whose fibers are copies of the group gamma sitting over P. So yeah, I mean, I don't know if you've seen this for the first time, whether it's obvious or not, but this is a really easy exercise. Maybe look at this slide in a quiet moment to see what exactly was going on and see that this is just an elementary exercise in just ordinary Chekhov cohomology theory. So just recast in this two group point perspective. But the point now is that once we're at this point, nothing stops us from now just raising the group point degree to any value. So we now have a definition of principal two bundles here. But just taking the previous picture, this neat formulation of ordinary principal bundles, and just generalizing it. So our Czech group point is still the previous Czech group point as it used to be. Now we can take any two group point, any two group. Here's our target. For instance, this automorphism two group. And form these pullbacks. And these will be the principal. These are the higher bundles. So that's the prescription. Let's look at some examples. Yeah, this is really, so if you put, I should amplify. If you really put an automorphism two group here, you just work out what this is. This is what Giraud originally defined as a non-abelian germ. It's this simple thing. It's just map to B odd, putting this back. But of course, yeah, maybe I don't know, any given reference on non-abelian gerbs that you open might offer something that looks more complicated. So here's the simple example that I was aiming for, which is supposed to highlight that all this yoga is a way of talking actually about twisted cohomology. So let's go back. Remember this simple example of the automorphism two group that I had highlighted at the very beginning, which was just a semi-direct product of BZ, two group, which is the delooping of the integers, acted on by the sign reversal. So that's a two group as we've seen, and now we can map into it, and we ask again that maybe we can project out this BZ two, Z-mod 2 copy here, and we could call this sigma. So as we've just seen, a map from X hat to some BZ mod 2 is actually a Z mod 2 bundle, principal bundle, which is a double covering of our manifold X. So underlying this two functor, I'm sorry, I have something. So underlying this two functor here is actually a double cover. We can project this out and call it sigma. And we get, if we unwind what this is in components, we get a picture that is very similar. In fact, it's the same kind of example as we had seen before in the discussion of group cohomology. Remember, there was an example at the beginning where instead of X hat here, we had BG, and then such maps were just co-targets in degree two group cohomology of G. Now it's essentially the same picture, instead of BG, we have the Czech group point sitting here. So the group elements that we're assigning here in Z mod 2 are no longer assigned to group elements here, but to double intersections. So we get group elements. If you compare this again to a textbook, And remember that this one edge here acts now by sign inversion on the integers that is this double arrow. And you see that this is exactly the Cherenkov cycle rule for degree 2 cohomology in what they call with local coefficients in our double cover. So such a two-functor, that's what I'm claiming here, showing here. That's what this exercise reveals. Such two-functors, for one of them, exactly the same thing. It's ordinary degree 2 integral cohomology of x with local coefficients given by our double cover. So it's a form of twisted cohomology, of local cohomology, but it's also just the principal 2 bundle for this structure group. So this is supposed to be this example which begins to illustrate in the first simplest case how zero gerbs, we've really described here in this translation a simple example of a zero gerb, which always seems to be something very esoteric and unconnected to anything else. But in this simple case, we see it's actually just ordinary twisted cohomology. And we can replace, keep playing here. Instead of the integers, it's going to be important for applications that I mentioned at the end to put the circle group. So in this slide here, you see I'm just changing the integers to the circle group. Nothing changes, only now that we're describing smooth Cherenkov cohomology with coefficients actually in the circle group. So this is now actually degree 3 cohomology with coefficients in the integers, again twisted. So up here in the title, I've started calling this Yandel gerbs without explaining much. But this is really, if you think of this as being gerbs, then these are gerbs on possibly unoriented manifolds twisted by the orientation double cover, which, I guess in some article that I've written with Urs Schreiber and Konrad Waldorf some years ago, is a kind of joke we call Yandel gerbs. But it's also just an incarnation of twisted integral cohomology. So that was the one punchline that I wanted to kind of walk through. So let me just read this out again because it's really important as the beginning of a story. So we've seen that non-abelian degree 1 cohomology is modulated by one stacks, by smooth groupoids like B gamma. This classifies, we've seen, gamma principal bundles, and gamma can be non-abelian. This is degree 1 non-abelian cohomology theory in the sense of Chanvel theory. We've seen that abelian second degree cohomology is modulated by 2 stacks, by smooth 2 groupoids such as the double delooping of A. And of course, it continues from here. Next, we can talk about degree 3 cohomology, degree n cohomology with coefficients in smooth n groupoids. To make this precise, one has to start talking really about Kahn complexes and stuff, which I didn't want to do for time reasons. It's kind of clear that one can keep going from. Another point is we've also seen the higher fiber or principal bundles are actually bundles of such moduli stacks. Right here, this thing was as a bundle over BZ2. This is a bundle of B2U1. But B2U1 itself is actually the moduli stack for gerbs. Or in the simpler case here. So these high bundles are actually families of modular stacks that vary over the base, and as such, they modulate cohomology, as these guys did, are now subject to global twists. So that's why this twisting comes in. That's this point I was trying to make. A higher bundle is something whose fibers are no longer sets with smooth structure, but higher stacks with smooth structure. But every higher stack is the modular stack of something. So in this way, higher principal bundles are moduli for some cohomology theory that twists around some base. Right, and now we haven't even talked about equivariance yet, but the good thing now is there's nothing much to be said in addition because we've already really dealt with it. Namely, I kept emphasizing codomains here that are groupoids and 2 groupoids, whereas our domain was really just a resolution of a manifold, which was this very discrete groupoid. So let's just allow the domain to be a general groupoid itself, and then everything is automatically equivariant, as shown by this example. Suppose now we have a smooth manifold X that is acted on by a group, a smooth, say a finite group to make it simple, or otherwise a properly acting group or something, acts smoothly on our manifold. Then there's a theorem, then there exists an equivariant good open cover, which in particular means there's lots of more properties one can ask for, but in particular it just means that the group actually acts in a compatible way on the disjoint union of all the charts. So we can take them all together, have the group acting here. And now we can form this data, we can turn it into a groupoid, into a two-groupoid, which I just made up this term, call it the equivariant Čech groupoid. So you see it has the edges as we used to do, that just remember that if a point sits in one patch, but also in another patch, then this is witnessed by this morphism here. But now this point can also have an image under the group action. And that can have an image under the group action. And so there's the action of the group here, reflecting that also these incarnations of points are all equivalent under this group action. And so this Čech groupoid, we have all these edges and everything is compatible with each other, meaning that if you transition here from one chart to the other, it's compatible with the group actions that this full three-dimensional structure here makes a two-dimensional commuting diagram. And down here, I should have maybe started here. Down here, we have just a plain action groupoid of G acting on X. We just have the points of X. We used to have just identities here if we were just in a manifold. Now, as G acts, we can have morphisms that witness this action that say, well, the point X is taken by G1 to its image on the group action. And we've thrown a morphism for this. We have this evident forgetful functor here. And as before, one can check using the rules of model category theory that this makes this equivariant Čech groupoid be a good model for this action groupoid. It's a cofibrillant resolution. So we can ask now, so what if we just replace what used to be our ordinary Čech groupoid here with this equivariant one and map it to any two group that may be acted on by our equivariance group G and look at smooth two functors here. These will now be assignments that take all this data on the left to data on the right. So it labels everything with group elements here and with higher morphisms with these two groups so that everything is compatible. Sorry. And so depending on what you want to do, you can just read off now what your equivariant Čech two co-cycle data is. And that is now the definition actually of equivariant higher two bundles. See, it's rather straightforward. If you forget what this means in details, we're just saying, well, there's some smooth two groupoid here sitting over BG, and it modulates whatever it modulates. And so it's the modular two stack for some notion of equivariant higher bundles. And namely, if you have any smooth manifold acted on by G, just look at the smooth two functors from here to there. And that any one such is the modulating data for such an equivariant bundle. So I can play the game I had before. I can form this EG and pull back to see what the actual bundle is like. And of course, you find that it's like an ordinary principal bundle or a higher bundle. Now, with some group action on the fibers, such that everything is compatible. You can just keep unwinding what that means. But that is the definition, the good definition. That's what it means in concrete local data. So this is as concrete as it gets. You see, this translation is really kind of powerful. This is a very abstract picture here. But using our model category theory, which tells us what the good representatives are, we can immediately read off what the good local data is that describes everything. So I guess I'm running out of time, but I'm also close to the end. As an example, I have this super simple, but actually very interesting example to offer here, just to give you a feeling for how things start. Suppose our manifold is actually just a point that is acted on trivially necessarily by some group G. Then if you just look at the previous definition, you see that this equivariant Čech groupoid is just BG again, right? Here, these morphisms all go away. If our manifold is a point, then this single X. And so we're just left with BG up here. And then if we take our structure group to be this projective unitary group, which I didn't mention actually at the beginning, I skipped over that slide. But suppose we take it. Well, when we have a group homomorphism, this two functor is essentially just a group homomorphism from G to PH. So it's a projective representation of the group G. And then you can start to play with it and say, well, what if this projective representation is twisted by complex conjugation and so forth? I guess I just come to an end here. There's some interesting structure in, if you wish, just the projective unitary bundles over just a point, which actually encodes exactly what people started to call the quantum symmetries of gaps. So that's one application here. I'm just mentioning this now as a random example here. We're one very simple examples of high equivariant bundles. One already sees very interesting, very useful structure. So this has a lot of application in some parts of current interest in mathematical physics. And of course, this leads over, if you've ever seen this before, this leads over to the discussion of, in this case, of twisted equivariant K-theory. I'll close here. I have the last slide that just says that proceeding along these lines, just gave these very simple examples. But if you just proceed along these lines and ask, well, for instance, is there anything that is fibered over this projective unitary group? Well, there's Fredholm operators. So the point of the slides is one gets very transparent, very nice models of otherwise rather intricate systems, such as, in this case, various twisted and equivariant versions of K-theory, which obtain a very neat formulation, just as more. So this all happens in smooth two-groupoids here, actually smooth groupoids, which obtain a very neat, simple, transparent, and yet concrete formulation in terms of this previous structure. Yeah, that's something I could go on here, but this is something we're currently actually working on. So there are some applications we think of twisted equivariant K-theory that haven't been fully discussed really yet in the literature. And maybe due to the fact that existing models are a bit opaque, a bit hard to handle, and one doesn't need our new model here to see this, but it sure helps. And we think there's some interesting applications there to stringy physics and some things. Yeah, that's what I had to say. I'll stop at this point. This is my last slide, but maybe we can see if there's questions.
One immediate question I had, throughout the lecture is, and also reading your new book, I should say, I'm not a preprint, but book, is that, the reason for just adopting this two truncation is not just expository convenience, but it's actually enough. We're working with homotopy 2 group, so we're working at the two truncated level throughout. And this is a kind of significant, not purely notational change from your earlier work. And in fact, one adopts the kind of higher bundle definition here is it's a kind of, it seems to be an application of how you adopt the theorem as a definition. So is that a correct impression?
Yes, yeah, that's a good point. Maybe I can, that's a very good point. Maybe I can briefly comment on this. That's right. So in that book we wrote, which carries the title Equivariant Principal Infinity Bundles, there's a general notion set up of untruncated higher equivariant bundles. But then we were interested in the classification result we prove happens to be a theorem just about ordinary truncated, if you wish, equivariant bundles, where the point was that by regarding them in this more general context, using some tools that become available in the more general context, we can prove something at least more transparently as was possible without. But through the bundles themselves at the end, just as in this example that is shown on the slide here, actually ordinary non-higher principal bundles. One point though is that due to the equivariance they enjoy, the equivariance is encoded in the higher structure, if you wish, right? That's one way to understand why it's good to go to this higher context. The punchline here is that if anything is equivariant, then it's actually secretly already something groupoidal, even though you might not have thought about it that way. So even if we just want to describe ordinary equivariant Fredholm bundles, say, it's useful to do so in the context of smooth groupoids. Yes. Yes. Which is not to say, though, I should add that one wants to stop here. So this just happens to be, since the equivariant theory turns out to be just very rich, it just happens that there's already a lot to be discussed just about ordinary equivariant principles. But of course, one wants to keep going from here and next discuss also more classification theorems of equivariant higher bundles. But we haven't done that. But there's nothing here to stop us. It's not like the theory wants you to truncate. It's just that that's where you want to start understanding examples.
Okay.
In fact, that's maybe this slide that I skipped over. was kind of concerned with. It illustrates, this example here was to illustrate that if we're interested, let's see, is it this example or? Oh yeah, here. So right. So if we're interested in SVR for this equivariant K-theory, if we're interested in projective unitary bundles, then since this projective unitary group sits in this exact sequence, then naturally it actually sits in a long sequence of higher groupoids, which involves this jerp here. It's an old fact that PUH bundles, so projective unitary bundles for the infinite in quotation marks unitary group acting on some Hilbert space, actually have the same classification as jerps, as these higher circle. So that's an important back and forth in discussing this twisted K-theory. That one has these ordinary groups, which to some extent are stand-ins for these higher groups. So that's one of these interplays, yeah, that are at work. Sorry, I'm not sure if I'm still answering your question, but
no, thank you.
Maybe, may I ask a question? Is it plausible to generalize this to super geometry by changing the Cartesian spaces to super Cartesian spaces? Maybe that's Fermat theory.
yeah, it's possible. What did you say, to change it to what exactly?
I mean, Cartesian, that there is the Fermat theory of Cartesian spaces that you use to define smooth groupoids, right?
Yes.
And also there is super Cartesian theories that
Did you say super? I'm just trying to.
Yeah, super. Yeah.
Yes.
Super.
Yes. No, absolutely. Yeah, absolutely. That's what I meant. That's exactly what we want to do.
Oh.
I mean, that's what I meant when I had this advertisement. Yeah, I said it's generalizable.
Ah, okay.
In fact, I guess that's if you go to the web page here of the talk, that's what I used to give talks about how to do exactly that, to go to the super space. So this is other talk I gave some years ago, Introduction to Higher Supergeometry, which is a very similar talk, which does exactly that. It replaces the Cartesian spaces by super Cartesian spaces, and then discusses. So here's pictures of two groupoids, and then discusses how we get notions of supergeometric higher stacks and groupoids, and how that can be made, how can be put to use in various contexts. Yeah, absolutely. That's what one can do. One can also use, which is maybe at least as interesting, one can also use, for instance, complex analytic spaces, Stein domains, and have a theory of holomorphic higher bundles and stuff. That's actually important for this application to equivariant K theory that I indicated.
Okay.
There's something about holomorphic twisted equivariant K theory which we feel has been missed, where the twisted equivariant K theory actually knows something about 2D conformal field theory by hypergeometric constructions. Yeah, that's exactly what one wants to do. One wants to generalize, replace the side by other sides. And much of the theory will just go through for any side. And then part of the theory will depend on the side being what I call cohesive. So this, for super Cartesian space and for holomorphic domains, and even for super holomorphic domains, actually the side is cohesive, and so even these theorems that we proved will still go through. If one takes yet more exotic sides like arithmetic or algebraic geometric sides, then cohesiveness will start to disappear, and some things will become, how should I say, more interesting, but also less well behaved. But anyway, yeah, all this can be done.
Is it 2018 talk in that page? You mean the related one?
You mean this year?
Yeah, no, I mean the one about super geometry generalization you mentioned.
Yeah, this was a talk I gave in 2018. Yeah, at this
Okay.
at
Thank
this
you.
meeting in Durham. I mean, if you're interested in this, there's also, I have very detailed lecture notes here in this series, Geometry of Physics. So categories and toposes goes through all the, it's actually higher categories and higher toposes. It goes through the details of these group points that I described. And then there's a lecture here on supergeometry, which describes how everything works with Cartesian spaces replaced by super Cartesian spaces.
Mm-hmm.
Yeah, you find all these links on the web page for this talk, so, which is also linked from your web page, right? If you go to your higher structure seminar, you find my talk there. Then it's this link that came out as @ talk slides and further pointers @. If you click on @ you come to this page.
Okay.
And from there you find all these other links.
Thank you.
Sort of something that seemed confusing in the diagrams that were defining the classifying space, or the boldface B operator, the commutative triangles. Or can you move to that slide?
Let's see, was it
or maybe just about the check condition? The transition map goes from the takes the ith chart into the jth chart through the intersection of the ith and jth chart. But then that means that first we restrict the domain of, I mean, if we're taking the example of function spaces, first we restrict it to a smaller domain and then embed that domain into a larger one. But then that means that we're taking some extension of a function, and whether the extension of the function may not be extended uniquely to a larger set. Does the non-uniqueness, is that something akin to what you mean by fluffiness? And then those, what should we make of those commutative triangles in that case?
right?
Or
so if I
am I misreading something?
If I understand your question well, so the answer is there's no such issue. But the point is, of course, I haven't given the formal definition of what these functors are, but we can easily understand it. The point is that this map here is three different maps. It's a map from the space of vertices to the space of vertices, from the space of morphisms to the space of morphisms, and from the space of two morphisms to the space of two morphisms. All these assignments are smooth. So the space of vertices here is the disjoint union of all the UIs, and the space of vertices here is just a single. So at the level of vertices, there's just a single map that takes everything to the point. Now the thing is, and I think this answers, if I understood you well, answers your question, is next there is a function from the space of morphisms to the space of morphisms, but the space of morphisms here is already the double intersection. So there's not a function on single intersections that is being extended or restricted. There is now just a single function on the space of double intersections to the space of morphism, which is gamma. So there's just a smooth function from double intersections to gamma. That's exactly the definition of a Chekhov cycle. It's a smooth function from the disjoint union of all double intersections to gamma.
Gamma here is
gamma is the group, the Lie group, the coefficient group. Yeah.
Ah, okay.
So if we would write this out, maybe I should have written this. This function is in degree 1. This two functor in degree 1 is a function from disjoint union over I and j of ui cap uj goes to gamma. This disjoint union of all double intersections is mapped to gamma smoothly, and that is really these functions, gamma ij max. They depend on point in double intersections. So this is an unconstrained, in degree 1, this is an unconstrained function, just any function to a group, and then the constraint comes only in degree 2. Now that function degree 2, the component function of the 2 functor, is to take the 2 cells here to the 2 cells here. The only 2 cells here are equalities. So this imposes now equalities on this, on the previously defined function. And that condition is exactly the one that is the Chekhov cycle condition, which says that gamma ij times gamma jk. So yeah, maybe this is what you're asking. So this happens on triple intersections. So this is for the restrictions of these functions. I see, maybe is this the question? So the function original, the Chekhov cycle, is defined on double intersections. Then for any triple intersection, you can take 3 ways of restricting the function of the double intersection to the triple intersection. There, these composites have to be equal. So it's really on the nose. I mean, that's the claim.
It's maybe the imposing the equality is sort of requiring globalizability or unique extendability of functions, or is it? Or
yeah, no, that equality says that function double overlaps, restricted in or pulled back in its 2 ways to triple intersections, has to satisfy this equality. Yeah.
Okay, but it's an external restraint that is not automatically specified, but then it would be restricting the ambient large function space. Or I mean, the example you gave us, C infinity ui into X or into Rn or something. So all the smooth maps from ui and open set ui into uj, and you take a function defined on ui, restricted on ui intersection uj, and then embed a function defined on the intersection to j, or do you go directly from ui to uj in some other way?
Are you asking? Yeah. Okay. So maybe, yeah, if we were at the board now, we would start unwinding the actual definitions. I haven't stated the actual definitions. Maybe that's your question. So what this thing really is, if you go to full definitions, this is a simplicial pre-sheaf on Cartesian spaces, which each Cartesian space assigns a simplicial set, which I was trying to indicate here, as such as is this, and this 2 functor is a homomorphism of simplicial pre-sheaves. If you unwind this, the claim is that the data in that map from here to there is exactly equal to the data of a Chekhov cycle. And I think you're asking how to see this, and yeah,
just checking the definition probably. So never mind.
Yeah, that's maybe a good. If you're interested, that's a good exercise to work on. So I haven't put it on the slide here, hoping it would be transparent this way. But yeah, I think the picture makes it really clear. Actually, that's exactly what's going on. But yeah, you should sit down maybe and.
No, it's not the unclarity of the picture or asking for an argument. I was just thinking if I accept that diagram and interpret it directly with the example you gave, then I should be able to map each function defined on UI to uj. That's what that arrow is, right?
You're asking here on the left?
Well, I mean, okay, I'll look at the slide and maybe email you. Okay. Any other questions?
Maybe I would have one question in the way of generalization program. My question is it possible to generalize the picture how we construct principal bundles once we replace ordinary manifolds as a base by some more general beasts like higher stacks or something like that?
You're asking what happens if we replace the domain the domain manifolds.
Yeah,
We make them
exactly.
stacks. Yeah, you see, this is really what this last bit was going into. Here, discussing the equivariant bundles, we indeed did that. We replaced smooth manifold with its quotient stack by some group action. But this is what this notation is really hinting at. That action groupoid is really the quotient stack of X acted on by the group. And so the statement is that in a G-equivariant gamma principal bundle is really just a plain gamma principal bundle on that quotient stack. And next you can ask, well, what if that stack isn't actually a global quotient? It could be it could be any stack. And yeah, it could be. Oh, my battery is running low. I might be offline soon. It's a pity. So yeah, indeed, you could have, the definition would still be the same. You could put any stack here, and then you would know what is the gamma principal on any stack. It's exactly that again.
It could be any infinity stack, right? I mean, it could be literally any element of an infinity topos.
Yes.
But the problem which immediately appears is that we have no such direct procedure how to obtain cofibrant resolution, right?
We do have. Well,
really?
Yeah, I mean, there's general formulas for cofibrant resolutions. So Dagger, for instance, in the context of proving that this condition is sufficient, which I mentioned here, he also proves how to universally solve it. It's just that always in model category theory, these universal formulas that always apply, they're usually unwieldy. So there is a formula that gives you a cofibrant resolution of anything.
Anything, okay. So
reference.
Yeah, so Dagger
effectively what you do the universal thing. You just take the simplicial resheaf that consists of all possible ways of mapping RNs into a given stack, just remembering them all. So it gives a huge simplicial set, but it's cofibrant.
I'm referring to your article which you wrote with Thomas Nikolaus and Daniel Stevenson about the presentation of infinity principal bundles, where you dealt only with classical manifolds as a base. So that was my concern, actually.
The survey paper on infinity bundles, principal infinity bundles, deals with the general definition over any element of any infinity topos. Yeah,
that's true. But once you delve into some computational questions, you need to say what's the cofibrant resolutions and stuff like that. So I thought before it's doable in this way. I mean, in Czech cofibrant resolution, only when you have a classical meaning one manifold as a base in this puzzle. But yeah, the reference on Dagger space article would be very useful for me.
Yeah, I'm back, by the way. Can you hear me? My computer battery went offline on my phone. Yeah, so this is a really good question. I indicated actually one first example of this generalization that you're hinting at. And you should already ask what is the cofibrant replacement of the global quotient stacks there. And then you need the theory of equivariant couples, of every equivariant good couples. Right. So this is the first step in this direction. You ask what is the tractable cofibrant replacement of a global quotient stack, and the answer is, well, you can take a good open cover that is actually compatible with the group action, and then form this what I call the equivariant groupoid. Right. This is the first step in this direction of finding more general cofibrant resolutions. And now, if you take any if you have some 17 stack that you would like to compute an equivariant 18 bundle on, you may have to do, apply some ingenuity to see if you can find a good covariant replacement. Yeah, there's general formulas, but there might not be a good formula. It depends. Yeah.
Does it have something in common with the Czech resolution technique? Like we are finding some good open cover and of anything, and then do the same job?
You mean standard Czech resolution techniques, like from?
Yeah. If it's similar to what you are referring to.
Yeah, so in some sense, I'm not sure if I understand the question, but in some sense, it's the model category theory explains what Czech cohomology really is and why, for instance, people go on about saying, oh, Czech cohomology only sometimes coincides with the correct chief cohomology, and and we can see it clearly here. We don't just need any Czech cover, we need a good one. It's the goodness of the cover that makes the corresponding Czech nerve be a cofibrant object.
Yeah. Okay.
And good Czech covers only exist under suitable conditions. So these standard conditions for Czech covering theory all turn out to be secretly ways of getting cofibrant resolutions without saying so. Yeah, that's a good point.
Yeah, thank you.
I don't know what Equivariant twisted KR theory is, but I would like to understand the kind of statement that you put on the last slide, because I mean I work on algebraic K theory and things like that a lot, not in the smooth category, but still, I mean, so such models like that are interesting. So just as a kind of elementary ignorant question, what's an algebraic model for KR theory? By algebraic, I mean like vector bundles on something type of statement, or like.
Oh yeah, so KR theory is just topological K theory with the complex conjugation evolution taken care of. So the algebraic model is complex vector bundles as before, but now with the Z-mod 2 action by complex conjugation, and and you assume that you evaluate on topological spaces that are equipped with an involution, with a continuous involution.
I see.
Such that they connect to each other.
I see.
So this is what Atiyah in 60 something called. He called it real K theory with capital R, which was maybe a bad idea because it gets confused with OKO, but that's what he called it. And so then KR theory became a word when people got sick of saying we're working with real K theory, but it's not what you think it means. Yeah, exactly. And
then you apply a truncation to the shape, the sort of the homotopy. So it's a kind of that's the shape operator. So I guess that gives you. I mean, I'm trying to unpack that statement because it's no longer here. But so the general principle there, because it's a very particular theorem, I guess. But maybe one can extract something about representability of K theory, because I'm interested in things like that. So I mean, ultimately, when I hear K theory, I think kind of so representability in terms of infinite, like some stack, not spectrum in this, as you said, maybe some spectrum object in some general sense somewhere. But so
yeah, absolutely. Mm-hmm.
So that's what the statement should be, right? I mean, underlying principle of that statement is a representability statement. Is that accurate?
Yeah, that's exactly what it is. It's just repackaged in a slightly non-standard way. So the truncation is just so tau 0 is just pi 0. This just means
sure.
Since we're looking at cohomology classes,
sure,
you could omit that, but yeah, this is so. And the shape just means, well, the shape is kind of important that it's outside of the mapping stack. The point is inverse. This just says that a class in the Swiss electron K theory is a relative or vertical homotopy class of sections of that bundle of Fredholm operators.
Oh, yes,
so it's really a rather usual statement. And it's absolutely a representability statement. It says that this bundle of Fredholm operators, Fred homotopy quotient by PU, that this is the representing space. Right. Here it's actually the representing bundle. And the usual way to think of it as a geomorphic type is to think of that bundle as its system of fixed points parameterized over the orbit category. That's how people will usually speak.
Oh, so that's what that notation indicates. With the you had like parentheses, and then you had this sort of. I thought that looked like co-invariance or something like that.
That was meant to be homotopies of these sections.
Okay,
so I didn't
okay.
in the slides I didn't show the passage for the orbit category. We discuss this in the book, in the last section of the book, the last chapters.
I haven't got there.
But yeah, this is actually a super important point, which I think is not maybe appreciated enough, even though this is well known in the sense that there's a handful of articles who say this and prove this. But when you go into equivariant cohomology, as you will know, people will go on about having to use genuine spectra, and that means you have to go to use transfer, and it means you're going in general quite far from the existence of an ordinary representing space.
Yes.
But K-theory stands out as actually having a representing space. As first proof, equivariant K-theory, I mean, as first proven by Atiyah, then more recently there were still proofs given by Fried and other people. But yeah, this is kind of known, and it's important in the sense equivariant K-theory is sort of naively, what they call naively equivariant. Yeah, this is really important.
Our time maybe is about to, there's a time limit for Zoom, so we need to wrap the discussion, but maybe a future seminar we can talk about it.
Yeah, future seminar would be very nice idea.
Okay. Yeah, all right. Let me know by email. We can think about it. Yeah.
Okay. Let's thank our speaker, and I'm stopping the recording.
Yeah, thank you very much for giving me the opportunity to speak. All right, see you then.
All right.
Thank
Thank
you.
you.